Welcome to this online presentation on understanding forest plots. I advise you to keep a print of a forest plot from a Cochrane review at hand. This may enhance the learning process as you will be able to relate and apply the presentation to the actual forest plots which you come across. The presentation starts with an introduction to forest plots and then deals with aspects of meta-analysis. Meta-analysis is the statistical method of pooling results from different studies. Meta-analysis involves extraction of secondary data from research papers, choosing the right statistical method, and finally interpreting the point and pooled estimates. Heterogeneity and subgroup analysis are aspects of meta-analysis that will be touched upon. First and foremost, why do we actually need to understand forest plots? We live in the information age and are loaded with tons and tons of material on any topic. Smart people seek answer to their clinical queries in secondary research rather than primary research. There still is numerous secondary research available today, and sometimes there is no time to read through the long texts of these meta-analysis. Forest plots not only provide a quick answer to the questions but are also very comprehensive. Just by looking at this graphical representation, I can immediately say a meta-analysis of 5 studies was done and it showed that the cure rates are better in the new drug, but the estimate of odds ratio lacks statistical significance. So what exactly are forest plots? A forest plot is a tabular and graphical representation of a meta-analysis. Whenever I get an original research article, I just look for the tables and graphs. The tables and graphs should be so comprehensive that just by looking at those, you should be able to tell what the entire study is about. In case you are interested, you go on to read the abstract and then the whole article if required. Similarly, just by looking at the forest plots, you should be able to tell what the entire meta-analysis says without going into the text. Evidence-based healthcare stimulates us to convert our clinical queries into PICO statements, where P stands for patient, I stands for intervention, C for comparison, and O for outcome. Just for example, we are doing a review comparing a new drug intervention with a standard treatment control. We have two comparisons under the review, that is in children and in adults. These are the different patient or setting scenarios. Each review may have one or more comparisons based on the criteria decided by the authors. The outcome measure is different in different studies, and sometimes a study reports more than one outcome measure. Meta-analysis shows different outcome measures in different forest plots. In this presentation, we will deal with two most common forms of outcome measures: dichotomous and continuous. Dichotomous is binary. That means the event either occurred or did not occur. In the example we have used, cure is a binary outcome and it is represented as the number of subjects cured out of the total number of subjects in each group. We have used change in quality of life as a continuous outcome, and the data is represented as mean and standard deviation in each groups. Now let us actually get into a forest plot and understand what they represent. Forest plot has two components: the table on the left hand side and a graph on the right hand side. Let us start from the left hand side along the details of study 1. In the new drug group, 15 out of 50 subjects were cured as compared to 10 out of 50 in the standard drug group. Please note that studies that have zero events in both arms are excluded from meta-analysis. This is the data that is extracted from the study and fed into RevMan, the software used for Cochrane reviews and meta-analysis. When the outcome is continuous, the mean and standard deviation along with the sample size in each group is noted. Study H shows that among 180 subjects in the new drug group, the mean increase in quality of life was 4.5 plus minus 1.5. And among the 200 subjects in the standard drug group, the mean increase in quality of life was 4.3 plus minus 1.2. Once the data is extracted from the study, there are different statistical ways of doing a meta-analysis. First, the analysis method may be either fixed effect or random effect model. Second, the different statistical methods are used for dichotomous and continuous data. Third, there are different ways to represent the effect measure. The effect measure for dichotomous data is either presented as odds ratio, risk ratio, or risk difference. Continuous data presents the effect measure as mean difference or standardized mean difference. In-depth discussion of these methods will be taken up in subsequent presentations. The meta-analysis, irrespective of the method used, provides us three values for each study: the weight of the study, the point estimate, and the confidence interval. The weight is represented as percentage in the column, and the total weight of all studies adds to 100. The point estimate and the confidence interval are presented together in a single column. 95% confidence levels are generally used. In the above example, odds ratio was the outcome measure for cure. Mantel-Hausdale method was used with a fixed model, and the point estimate and 95% confidence intervals was created. Study A shows an odds ratio of 1.71 and a confidence interval of 0.68 to 4.30. Each row in the table represents the details from one study, and now that we understand what each of these values mean, you will understand the graph easily. Each line in the graph is a representation of one study. The blue square represents two things. The position of the blue box represents the point estimate. In the study A, the point estimate is at 1.71. The size of the box represents the relative weight of the study. Thus, study F has the biggest square because this study has the maximum weight. For study O, the point estimate is as the line of no effect, representing that both groups showed same response. Nearly all studies will show point estimate to be on one side of the line, and the labels below help us interpret the meaning of each point estimate. The labels are placed depending on whether the outcome measure is beneficial or detrimental. Study A and F favor new drug as there are better cure rates with the new drug. Study K and N have a point estimate of odds ratio on the left hand side, that is, standard drug showed better cure rates. The arm of each study represents the confidence interval. If the arm crosses the line of no effect, there is no significant difference between the groups. Since a 95% confidence interval is used, if the arm stays on one side of the line of no effect, it can be interpreted that there is a significant difference with a p-value of less than 0.05. The diamond in the meta-analysis is the most important as it represents the point estimate and the confidence interval of the pooled results. In the above example, the pooled odds ratio estimate is at 1.15 with a confidence interval of 0.89 to 1.47. Since the diamond crosses the line of no effect, it can be said that though the meta-analysis results favor the new drug, the estimate is statistically not significant. It is also evident from the p-value for the test of overall effect, which is 0.28 for this meta-analysis. P-value greater than 0.05 will mean that there is statistical not enough evidence for a difference between the two groups. Please note, clinical significance is different from statistical significance. The lines in the forest plot may be scattered all over as different studies show different results. High variability in the results make it difficult for us to take clinical decisions despite the fact that pooled results may show significant difference. Thus, it is important to measure the heterogeneity among the studies. The chi-square test for this meta-analysis gives a p-value of 0.01, indicating that there is a significant heterogeneity. The I-square is another measure of heterogeneity, and I-square values greater than 40% needs to be investigated. In the above example, when we investigated the heterogeneity, we found that studies of shorter duration had similar results and those of longer duration similar results. Thus, a subgroup analysis was performed. You may note that the heterogeneity in subgroups are reduced. With this presentation, I hope you will be able to read forest plots better. I thank you all for listening to this lecture patiently. For further reading, please visit the Cochrane Library and the Cochrane Collaboration websites. I will be happy to receive feedbacks from your side on this presentation and other notes. I will also be happy to respond to any queries which I can. Thank you.